Welcome to G Fun Facts Online. Think about the last time you were in a museum, looking at a pot or a tool from thousands of years ago. It sits there, silent. But what if it could talk? What if the clay of that pot held a hidden signature that could tell you the exact riverbed it came from? What if a metal axe could reveal the specific mine, hundreds of miles away, that birthed its ore? This isn't science fiction. This is the revolutionary field of archaeochemistry, a science that is fingerprinting the past and unmasking the secret trade networks that built our world. At its heart, archaeochemistry is about reading an artifact's chemical or isotopic fingerprint. Many natural materials, like clay, stone, or metal ore, have a unique geochemical signature based on the specific geology where they formed. By matching an artifact's fingerprint to a database of known sources, we can trace its journey from origin to discovery, turning a simple object into a data point on a map of ancient interaction. So how exactly do scientists read these invisible signatures? They have a powerful suite of tools, each offering a unique window into the atomic world of an artifact. One of the most popular is X-Ray Fluorescence, or XRF. Its biggest advantage is that it's usually non-destructive. Portable XRF analyzers look a bit like a price scanner gun, and they allow scientists to perform analysis right there in the museum, or even in the field. The instrument shoots high-energy X-rays at the artifact. This excites the atoms inside, causing them to release their own secondary X-rays. The energy of these secondary rays is a unique signature for each element. The machine reads these signatures and gives a complete breakdown of the artifact's chemical makeup. XRF is fantastic for materials like obsidian, a volcanic glass that was the black gold of the Stone Age, used for ultra-sharp tools. Different volcanoes produce obsidian with unique trace elements, so a quick XRF scan can match an arrowhead to its parent volcano, mapping out incredible prehistoric trade routes. But what if you need to detect elements in microscopic amounts, or measure the precise ratio of an element's different forms? For that, scientists turn to mass spectrometry. A powerhouse technique is called inductively coupled plasma mass spectrometry, or ICP-MS. Here, a tiny sample of the artifact is dissolved and blasted with plasma, a superheated gas hotter than the surface of the sun. This vaporizes and ionizes the sample, and a spectrometer then sorts these ions by their mass, providing an incredibly precise and sensitive reading of over 50 different elements at once. An even more advanced version is laser ablation ICP-MS. This is the minimally destructive option. A high-powered laser zaps a microscopic spot on the artifact, often no bigger than the width of a human hair. The vaporized material is then swept into the mass spectrometer for analysis. The damage is virtually invisible. This precision allows researchers to analyze the glaze on a pot separately from the clay, or even individual mineral grains. In one study of Caribbean pottery, LAICP-MS identified 9 distinct production areas, revealing long-distance trade routes between islands that spanned more than 1,000 years. Another key technique looks not just at which elements are present, but at their different atomic weights. This is isotope analysis. Isotopes are atoms of the same element with a different number of neutrons. For archaeologists, the beauty of isotope ratios is that they often aren't changed by processes like melting or firing a pot. They are a permanent, unchangeable signature. The gold standard here is lead isotope analysis. Lead has 4 stable isotopes, and the ratio between them varies depending on the geological age of an ore deposit. Crucially, when you smelt that ore and cast it into a bronze axe or a silver coin, the lead isotope ratio doesn't change. It's a direct fingerprint of the mine. By comparing an artifact's signature to databases of known ore deposits, researchers can pinpoint the exact mining region that supplied the metal, revolutionizing our understanding of the metal trade in the Bronze Age and Roman Empire. Finally, not all fingerprinting is high-tech. Ceramic petrography is a geological technique where scientists examine a paper-thin slice of a pottery sherd under a microscope. This reveals the ceramics fabric. the clay matrix plus any tiny bits of rock or minerals. A trained petrographer can identify these mineral inclusions, and since minerals reflect local geology, they can often trace the pottery back to the area where the potter dug their clay. This doesn't just reveal the origin, but also the technological choices the potter made. Now, let's see these techniques in action. The true power of archaeochemistry comes alive in the stories it tells. Let's start with obsidian, the black gold of the Stone Age. In the Mediterranean, there are 4 major island sources of obsidian. By using XRF to analyze thousands of obsidian tools found across Italy, France, and North Africa, archaeologists have mapped the distribution from each source. These maps show not just the movement of a valuable material, but they also testify to the sophisticated maritime skills and social connections of Neolithic communities, long before the great classical civilizations. The story is even more dramatic in North America. Obsidian tools found in Alberta, Canada, were analyzed with XRF. The results were stunning. The obsidian wasn't local. It came from sources thousands of kilometers away in Idaho, Wyoming, and British Columbia. This proved the existence of vast trade routes crisscrossing the continent for millennia, connecting diverse indigenous groups and shattering old ideas of isolated regional cultures. While obsidian was a luxury good, pottery tells a more everyday story of culture and commerce. Because clay is heavy, potters usually used local sources. So when a pot is found far from where it was made, it's a direct marker of trade. It might have been traded for its own beauty, but more often it was a container for things like wine, olive oil, or grain. The study of Roman amphorae is a perfect example. These large jars had distinctive shapes that hinted at their origin. Chemical analysis confirms these origins, allowing us to map the distribution of Spanish olive oil or Gallic wine across the entire Roman Empire, revealing the staggering scale of Roman commerce. An even more incredible case comes from Pavlopetri, a submerged Bronze Age city off the coast of Greece. Using petrographic analysis on pottery recovered from the seabed, researchers identified mineral inclusions that linked the pots directly to Minoan Crete. This was tangible proof of maritime trade and cultural links between the mainland and the powerful Minoan civilization 500 years ago. A story told by broken pieces of pottery from the bottom of the sea. The arrival of metals changed human history, creating new technologies, powerful weapons, and complex economies. Tracing these metals unravels the supply chains that fueled entire ages. The Bronze Age itself is defined by an alloy of copper and, crucially, tin. Copper sources are fairly common, but tin is geologically rare. For decades, the source of the tin that fueled the great empires of the Near East was a huge mystery. Using lead and tin isotope analysis, researchers are finally solving it. The evidence now points to a vast, interconnected network drawing on tin sources from Central Asia and perhaps even as far away as Cornwall in Britain. Imagine that, a truly globalized world more than 3,000 years ago. Finally, let's look at the grand monuments of the ancient world. The white marbles of the Aegean were prized for their beauty. Using isotope analysis of carbon, oxygen, and strontium, scientists can identify the unique fingerprint of each major quarry. We can now say with certainty that the Parthenon in Athens was built almost exclusively with marble from the nearby Mount Pentelicon. When we find a Roman statue in North Africa, we can determine if it was carved from local stone, imported Italian Carrara marble, or prestigious Greek marble. This reveals the economic reach of an empire, the tastes of its citizens, and the incredible logistics required to transport massive blocks of stone across the sea. But these scientific techniques are not just about drawing lines on a map. They are about understanding people. The movement of goods is tied to the movement of ideas, technologies, and beliefs. The vast quantities of Roman amphorae suggest organized, state-level trade. In contrast, the way obsidian tools become scarcer the farther they are from their source suggests a more informal village-to-village exchange network. The presence of exotic materials, like lapis lazuli from Afghanistan in an Egyptian pharaoh's tomb, wasn't just about having a pretty blue stone. It was a statement of power, wealth, and the elite connections needed to acquire it. The science even connects us to the individuals themselves. Sometimes, ancient potters left their fingerprints in the soft clay before it was fired. These prints are so well preserved that their ridges can be analyzed. By measuring the ridge breadth, archaeologists can estimate the age and sometimes even the sex of the person who made the pot, telling us if it was the work of men, women, or children. It's a profoundly human connection, a touch frozen in time. The field isn't without its challenges, of course. Some geological sources can have similar chemical fingerprints. And the ancient practice of recycling metals can mix different sources, creating a composite signature that's hard to decode. But the science is constantly evolving, with new techniques and larger databases making the results more reliable every year. In the end, archaeochemistry has allowed the silent artifacts of our past to finally find their voice. It has revealed a world far more interconnected, dynamic, and complex than we ever imagined. It shows us the life story of an object, from its geological birth to its creation by an artisan, its journey across land and sea, and its final use in a distant land. The next time you walk through a museum, look closely at that silent stone tool or clay pot. Remember that locked within its very atoms is a hidden map, a chemical signature telling a remarkable story of human ingenuity, mobility, and our enduring quest for connection.